To support our discussions with the world's leading thinkers, please see the video description or visit eism.eu/support. Thank you.
Hello and welcome to A Theory of Everything. I'm Jose Luis Razo Bravo, the Executive Director of the European Institute of Science and Management. Today we have the privilege of receiving another visit from Professor Avshalom Elitzur. He is an Israeli physicist and philosopher. He's a professor at the Chapman University, and he's also the founder of the Israeli Institute for Advanced Research. This is his second time on the channel, and we've had the privilege of having him on for the first time, where he elaborated on one of the ideas that perhaps he's most noted for, which is the so-called Lev Vaidman bomb testing problem in quantum mechanics. Some of our viewers may be familiar with the channel of Sabine Hassenfelder. Sabine Hassenfelder, with reference to the bomb testing experiment, said that many people think that she believes that quantum mechanics is not strange, and she argues that quantum mechanics is not really strange. The kinds of things that we normally think about with quantum mechanics, like entanglement, superposition, these things aren't strange. She says what really makes it strange is you understand the Elitzur Vaidman bomb testing experiment. That's what makes quantum mechanics really strange. So in his first public lecture, which we had the privilege to host for our channel, he argued, and I coincide with his argument, that the bomb testing experiment, or what's more formally known as the interaction-free measurement, is a very valuable introduction to quantum mechanics. And what he provides through this public lecture is a very valuable service to the public and to our viewers to understand quantum mechanics through the interaction-free measurement. And I completely agree with him that this is a very valuable, empirically fruitful, very pregnant with meaning and potential to understand quantum mechanics and a new realm of physics that is opening up to us. So I highly encourage you to take a look at that video, that public lecture. And in this lecture, we're going to talk about, Professor Elitzur is going to talk about the thermodynamic foundations of organic life in one part, and then he's going to introduce us to a very new set of ideas, a hypothesis about the ski lift pathway and the role that thermodynamics and complexity theory has in biology and evolution. So these are all very, very valuable ideas. And Professor Elitzur, thank you so much for sharing these ideas with us, and welcome back to the channel.
Thank you very much, dear friend Luis. It is really a privilege to be in this respectable forum. So the subject which I'm going to introduce is a meeting between two branches of science, actually two ways of looking at nature, which look opposite to one another, but then it turns out that they complement one another in a very fruitful and beautiful way. Thermodynamics is a branch of physics dealing with energy, manifestations of energy, changes of energy, and so on, and related concepts. Biology deals with life. And this brings to us, I would say, once we talk about physics and biology, especially when we talk about theoretical physics, we recall that actually these two disciplines are very different in one respect. When I'm talking about theoretical physics. In theoretical physics, you try to simplify things, make them as simple as possible. and you deal with a single particle, you deal with, you make an experiment, you think about a system where there is no friction, there is no error, there is no gravity. You try to simplify as fewer components as possible in order to understand the law of nature. And then you go to the more and more complex phenomena. Of course, we do have nonlinear physics and chaos physics and so on, but theoretical physics is always looking for the simplest principles, the most basic principles, which means that usually we discuss the simplest situations. You can't do that in biology. In biology, the very idea is that you're dealing with extremely complex phenomena, which means that you have to go and study all the details, whether it is of botany, zoology, biochemistry, and so on and so on. And what I want to show, may I begin with a joke, in order to just stress the difference between the two disciplines. This is the story of two scientists who were sentenced to death, a physicist and a biologist. And before executing them, they asked them, what is your last wish? So the physicist says, for many years, I have a theory which explains life. So now I would like to have a seminar here to present my theory before you guys kill me. And they say, fine. And then they ask the biologist, what's your last wish? And he says, I'd like to be executed before my colleague gives his lecture. So, and we can understand why. Whenever a physicist tries to say something about biology, people say, look, you don't understand anything. It takes you years to study endocrinology, to study biochemistry, cell biology. You have to go into the details. Forget about it, saying something general about it. And mostly they are right until we come to this branch of physics, which is thermodynamics. And there is something very nice about thermodynamics. Its laws, the laws of thermodynamics, are ubiquitous. They hold for all kinds of systems, no matter what kind of matter they are composed of. They can be made of iron, gold, clay, whatever. And it doesn't matter what kind of energy goes through them. So it could be an electric engine or an airplane or an elephant. So you see, life is also included in this because all living systems are kind of machines. And if thermodynamics can say something general about a certain system without going into its details, it may be relevant to biology too. Then I'll give you one more example in thermodynamics. When you go to the patent office and you say that you have an idea for a machine that is a perpetuum mobile, the patent office in all countries, they're going to say, we are not going even to consider your patent. And you say, why not? I'm a physics professor. Look, it's very complicated. You didn't go into the details to see that I'm correct. And then they say, we don't care about the details. If you think that you can violate the first or the second law of thermodynamics, we believe that they are valid. We are not going to go into the details of in order to see what's wrong with your idea. So this is something very powerful. And here is the case where, as a physicist, when you come to talk with biologists, I believe that you have something interesting for them. You can add to their knowledge, they can add to your knowledge, and there could be a fruitful meeting between the two disciplines. So I'm beginning this, and I apologize to those of you who have taken this course or still remember it from the undergraduate studies. Just a very brief introduction to thermodynamics. So why is thermodynamics relevant to life sciences? I say the following. It studies energy and entropy transformations, regardless of the system's chemical composition and type of energy. More interesting, so its jurisdiction is ubiquitous, whether it living systems or inanimate systems. Then thermodynamics deals with entropy and order, which is related to it, and which means that it also deals with information and complexity, which are also hallmarks of life. So this makes it highly relevant to biology. So here I'm going to introduce the 4 laws of the four laws of thermodynamics. And I'm going to dwell only on one of them, which is relevant for us, but I'll just mention them. So you all know the first law of thermodynamics, which says that energy is conserved, just like matter. Energy is not created anew. Energy does not vanish. Energy in any closed system remains the same, just as matter. Yes, in relativity, energy and matter will turn into one another, but for our purpose, the first law of thermodynamics is the conservation of energy. The second law of thermodynamics is opposed to the first in that it has a kind of time error, and actually it tells you about something which is not conserved. If you have a closed system, matter is conserved, energy is conserved, everything is conserved. Entropy can only go up. It will never go down by itself, which is something very interesting. Of course, now we have to explain what is entropy, and it will take a portion of this talk, and it will be very interesting. I mentioned two other laws just for completeness. You can't, the third law, which is not relevant for this talk, is that you can't come to the absolute zero by a finite series of processes. I said that there are four laws of thermodynamics. I presented the first, the second, the third. Which comes next? Some of you probably know it's not the fourth, but it's the zeroth law, which is very basic, and it is actually kind of has a logical ring, and it has been formulated after the first three, but because it is more fundamental, they made it the zeroth, and it tells you that if two systems are in thermal equilibrium with the third, then they are in thermal equilibrium with one another. So this is the kind of law on which you can build the other formulations of thermodynamics. As I said, we are interested mainly in the second law, which talks about entropy, and we want to discuss entropy. One more thing, you know, this presentation is copyleft, sorry, as you could see in the first slide, which means that there is no copyright on it. I myself took it from various sources, so everybody can download it. Luis will have a copy for everybody who asks. If you want to follow this lecture in more detail, then the presentation is available for you with a good, I compiled also a good bibliography of relevant references. So I'm going to skip some of the, this is due to my colleague, Professor Cohen, from, now he's in Bar-Ilan University, about the laws of thermodynamics. I'm going to skip this one and this one too. And let us go to the definitions, to the textbook definitions. We want to know what is entropy. And I'm going to take visual, I'm going to focus more on visual examples. Later you can comprehend better the mathematical formulations following them. So here's the first. What is entropy? Entropy means equilibrium. In this case, you see a very simple, I told you that physicists like to have simple systems. So here is a very simple system. I have a box divided into two. There is a partition. There is gas on one side and vacuum on the other side. And now I make a hole in this partition. I still have only gas on one side, vacuum on the other, but in time, I'm going to have the gas, you know, imagine all these molecules running to all directions, colliding with one another randomly. This is how gas spreads and goes through the hole and fills the whole box. So here we have full equilibrium. So let me repeat, here entropy is very low. Here it is higher, and here it is at the maximum. You have an equal amount of gas on both sides. So one definition of entropy is equilibrium. When equilibrium comes, when you have full equilibrium, entropy is maximal. Let me say from the beginning, you know, many teachers, many instructors, professors of thermodynamics have different approaches how you should teach thermodynamics. And most of them say, never listen to my colleague. The way he teaches it is completely wrong, and they are misleading you. What I'm going to do is bring all the definitions, all the measures, and show how they intuitively, very nicely fit with one another. So don't worry if you somebody told you that this is not a good explanation or illustration of the second law. Let me say something very important. When we are talking about equilibrium, we are talking about equilibrium in two senses. It could be equilibrium in matter, as you see in the upper example. All the gas is in one side, and there is vacuum on the other. So it is far from equilibrium, and in time, it will come to equilibrium, and entropy will be maximal. Entropy equilibrium can hold in terms of energy. Suppose that you have an equal amount of gas on both sides, but on one side, the gas is hotter. In physics, we usually denote velocities by arrows. So you can see that at the left side, you have very fast molecules, which means that there you have a hot gas. And on the right-hand side, you have cold gas. In time, you're going to have lukewarm gas on both sides. That is, that from all the collisions of the molecules, you're going to have an average intermediate range of velocities. So these are two senses, and it's important of entropy. It could be either or both in matter and or in energy. Here is the case in which entropy is the highest, and I should have shown in the lower illustration how the arrows become are getting an intermediate length. So just to give you an example, here you can see gas turning into liquid and turning into a solid, or even to a crystal. So some people say, you see, the second law is not always correct. You had a disordered state of gas, all these molecules. Then when it cooled into liquid, they are closer, and then they form a solid, which is very ordered, or sometimes even a crystal. Let me remind you why this does not contradict the second law of thermodynamics. So here again, the distinction between matter and energy is important. When you get a crystal, you have a higher order of the matter. The molecules now come together and they are closely attached to one another. They form one crystal. What you should take into account is that energy is now much less ordered. The whole solution has cooled down. A lot of heat was released to the environment, so a lot of photons have escaped. So in terms of energy, entropy has gone up again. So this is an illustration, which a kind of caveat, which tells you that when you are looking for an ordered or disordered state, look not only at the matter, at the atoms, but also at the energy, at the heat, at the radiation. During solidification, atoms become spontaneously ordered, but kinetic and chemical energy are radiated out as heat. So overall entropy has therefore gone up. Here you can see what happens when you are making a crystal. This is the same idea. Heat is released to the environment. Entropy as irreversibility, I'll just skip this for simplicity, and the Carnot cycle. And here is another thing that I want to say. Here is where the two laws of thermodynamics have a say. We know that thermodynamics is concerned, which means that energy can be transformed. Kinetic energy can be transformed into electric energy, which can be transformed into electromagnetic energy, and so on and so on. If we look around us, we see all kinds of transformations indeed. But here comes the second law. So this is the first law, and there is a measure called joule, which tells you just how you can convert one kind of energy to another kind of energy, how much kinetic energy can turn into how much heat or how much radiation, and so on. So energy is conserved. This is the first law. Now comes the second law and says that one thing is not conserved, and then this is the entropy of the energy. Let me explain that. This is a kind of engineer's perspective. We humans love to take energy and to perform work by it. Fine. Not all the energy is turning into work. Some of it turns into another kind of energy, which is heat, which engineers do not like and technology does not like. With heat, you can do very little or actually no work at all. So when one kind of energy is transformed into another and then into another, this is the first law, which says that they are conserved. But here comes the second law and has a say. And it says that they will degrade from the most usable kind of utilizable kind of energy to the least useful one, which is heat, which is bound energy. So you have free energy and bound energy. Let me give you an example. You can see a rock just falling down from the mountain and then falling down. So all the kinetic energy has turned into heat. You will never see the reverse is occurring. So all kinds of, we have to remember that all kinds of energy eventually turn into heat. And then you can't do work with it. Now, some students usually ask, why do you say that you cannot perform work with heat? We came here by car, which means that there was a lot of heat in the engine, and because of the combustion, this has moved your car. That's important. The system, in this case, the engine, the car, is far from equilibrium. You have a hot reservoir and cold reservoir, which is the environment. This way you can do work. Imagine when you are in a closed room and you have all the heat that you want, thousands of degrees, but it's in complete equilibrium. How much work can you do with it? Zero. You are surrounded by energy, but you can't do any work with it because this is heat. If you have a cold reservoir to which you can attach your system, then heat goes from the hot to the cold, and in the middle you can do work with it. But as long as this is a closed system, heat means that the energy has the maximum entropy. These things will become clear in what comes later. Here is another illustration, high school illustration, but it will help us later. You can see here when we are talking about order. So you can see here an ordered state. You have all the balls before the collision in a triangle. Energy is also ordered because all the energy is concentrated now in the ball that you are going to shoot into this triangle. You shoot the ball, and then all the balls now disperse to all directions. All of them have little kinetic energy, so energy is now divided between them. They are not ordered. So here is a manifestation of the second law of thermodynamics. From an ordered state, you went to the disordered state. Somebody can be smart and say, let us reverse it. I'll put many technicians, many students, and I'll instruct them. I'll make the calculation how you can take all the balls and give each of them the exact push, just the reverse push that they received from the initial state. And then if you do that, you reverse all the velocities, and then you may get your nice triangle back, ejecting back your original ball with all its energy. You can do that. But at the end of the day, you look at your laboratory and you see that the entropy of the laboratory has gone up. And it has gone up more than the entropy decrease on your billiard ball. So the overall entropy has gone up. You want to repeat the process and have your laboratory cleaned at the same time and remaining ordered at the same time. At the end of the day, your entire department, the department chairman comes and says that there's been more entropy in the department. And if you ask his collaboration, then the dean comes and she will say that the entropy of the faculty has increased, and you understand how you go more and more. So for every system, you can decrease the entropy within it, but then it will not be, you have to turn it into an open system, such that energy can come from outside in order to reverse it. But then because this is an open system, your next closed system is going to have, again, entropy going up. So this is the kind of commandment. You can't fight City Hall. Entropy must always increase. This is a paradox, a philosophical one, but has very interesting physical implications about the error of time. This is a paradox which was pointed out by Loschmidt to Boltzmann, one of the founders of thermodynamics. And Loschmidt asked Boltzmann, you remember the example of the box with the two halves with equilibrium going up, and then we say that entropy is going up. Loschmidt asked Boltzmann, what happens in this intermediate state? What is going to be the future of the system? And Loschmidt, of course, said, yeah, it's going to be much more disordered. That is, you're going to have the gas being evenly spread on both sides, and entropy will go up. Then Loschmidt asked him, can you tell me what is going to be the past state of this system? Boltzmann used his equation, his mathematical formulation, which deals with probability, and Boltzmann said intuitively, in the past, it should be much more ordered. Then Loschmidt asked him, he said, your formulation, which is a mathematical one, we will show it in a minute, is talking about the probability. And you say that it is much more probable in the future to have the gas evenly spread. But then you should say the same thing about the past, because mathematics is completely indifferent to the two time directions. So if you think that only with mathematics you can explain the origin of time asymmetry, you are wrong. You understand, there is something very interesting here. Each of the molecules' collisions can run backwards. And by the laws of physics, everything is okay. The basic laws of physics are invariant to the direction of time, just as they are invariant to right, left, north, south, and so on. The laws of physics are invariant in space. When you're talking with basic interactions, the laws of physics are also invariant in time. You run it by video, forward or backwards. As long as you have only two molecules, then you can distinguish between what is going normally and what is going backwards. How come that from all time symmetric molecular interactions, you get this time asymmetric? This is where Boltzmann failed. He intuitively said that if you go to the past, then you must have it more ordered. And Loschmidt said, no, by mathematics, you should also say that the past has been more disordered, so which means that sometimes order increases and entropy goes down. This has been a paradox. It kind of remains a paradox to this day. So let me tell you, this was Boltzmann, one of the pioneers of thermodynamics, and among the people who formulated the second law, who unfortunately ended his life by suicide. This was Paul Ehrenfest, who continued Boltzmann's work, and unfortunately he also committed suicide. This is Robert Mayer, who formulated the first law of thermodynamics, and because there was a dispute whether it was him or Helmholtz, he also tried to commit suicide, but he luckily survived. So I beg you, if you think too much about thermodynamics and if you think about a certain paradox, here is my phone number. Don't take it too seriously. So this is the second law, and now let me tell you, when we are trying to define or measure entropy, there are various authorities, and these are very distinguished professors who have different opinions how you should teach the second law of thermodynamics and what is entropy, whether you should use disorder or you should not use disorder. Rather than going into the debate between them, here is my ruling. They're all correct. When I teach thermodynamics, I take all their approaches, although you think that they conflict one another. I'm going to show that intuitively they all give you a coherent picture, and it's good to teach all of them together. So here it is. I'm going to give you a few measures of entropy, how you measure it, how you define it. I'll begin from the mathematical ones and then proceed to the physical and even to the technological ones, and you will see how they complement one another. So what is entropy? First of all, entropy is disorder, and this is a very intuitive notion. Everybody knows it, even if they don't know physics or mathematics. You can see two ways of having your clothes in the closet, and I think that everybody will agree, even if they don't know anything about physics or mathematics. On the left, you see a highly disordered closet, and on the right, you see an ordered closet. So this is intuitive, but mathematics can actually formulate it. Why we say that the right, that the closet on the right is more ordered. So another definition of order is randomness or probability. And later we are going to have another slide which is going to give you mathematical definitions of what is order and what is disorder. You can see here, I'm going to use sequences of digits. So obviously you can see that sequence A is maximally ordered, sequence B is, I can show you maximally disordered, C and D are something more interesting, and you can see some mathematical definitions, which I'm going to talk about later, divergence from equiprobability, from independence, redundancy. So we can measure orderliness by mathematically by the relations, whether in time or in space or in any other way between the system's components. So this will be our second definition. Third one, we already know it, and this is equilibrium. So you remember, there is little equilibrium in the upper system. Later, in the lower figure, you have greater equilibrium, maximal equilibrium. So entropy has gone up from the upper to the lower. As you see, you can now understand why you think that the closet on the right is more ordered. Imagine a closet where you ask, where is my shirt? Or where are my pants or my socks? And people tell you in this closet, you have the same probability of finding your pants or underpants or whatever in each of the compartments. You don't like, this is not what you call order. Order means that all pants are on one side, all shirts, all sweaters are on the other side. So you can see that the intuitive notion of order fits nicely with that of equilibrium. Now comes the idea of Boltzmann, and he says the following. S is a function of k logarithm, a natural logarithm of W. W is the important thing here. You have a macro state, which is the whole, let's take this box with gas. You have the whole macro state, which is box in a gas, and you have a micro state, which means the precise position and momentum of each of the molecules. Now, think about how many ways there are to have a low, something far from equilibrium, many, but how many arrangements of the molecules are possible in order to have high equilibrium, orders of magnitude greater. Look again at the upper example of the closet. There are several ways of making a closet ordered. Put pants here, shirts here, socks here, or vice versa, or whatever. So there are a few ways to make it ordered. To make it disordered, there are zillions of arrangements. So this is the beautiful expression of Boltzmann, that S, entropy, is a function of the W of the number of arrangements, which is relatively small when you are talking about ordered states, low entropy state, and very large when you are talking about disordered, high entropy states. Irreversibility, so that's interesting, and you already know it. You can imagine, actually, it must happen, that when you begin with the lower equilibrium, you open you make a hole in the box. In time, it will go only in one way, and the the disequilibrium, far from equilibrium, will approach equilibrium. Entropy will go up. This always happens like this. You will never see, when you're talking about many molecules, you will never see spontaneously a box with equal amount of gas or equal amount of heat, and all the molecules just by chance converging and going to the other side. So now intuitively, you can understand when you see a burning candle, you will never see a burnt candle just, there is some kind of fire which brings back some particles which were burnt and make them again and give you an unburnt candle. In terms of energy conservation, this is possible, but it is impossible in the terms of irreversibility, just as you cannot expect all the molecules of the gas converge by themselves just by accident going to the left. Dissipation of heat, so that's another way, and this is that the difference in entropy is the difference in heat divided by the temperature. So here you have heat inserted into this system. I'm giving you the second example of entropy. So you have hot on one side and cold on the other, In time, it will become lukewarm. So this is the temperature. You have to divide it by the temperature, and you see that the amount of entropy has gone up. Decrease of energy is efficiency. You remember that I say that energy goes from the more efficient one, from which you can do a lot of work, to the less efficient one, which is heat, from which we cannot do any work. So in the upper case, you can see that you have pressure. Has this partition been a piston, you can do work with it. It will be an engine. Whereas in the lower example, I mean, all the energy is now dispersed between the molecules, and you cannot make any heat of it. The other measure of entropy is ignorance. Some people say, I don't like it very much. If you can't describe the details of the system, that means that its entropy is high. But if you can describe it, it means that it's low. For example, if you say that a certain matter is a crystal, actually in one word you have given a good description of where are all the molecules. Whereas if it is in gas, then you're ignorant about it. I am not very happy about that, but I'm mentioning it only for completeness. What I hope I have convinced you, and you can later think about it yourself, so test it yourself. You have different views of looking at entropy, and you can see that they are all compatible with one another. They all complement one another. This has been our introduction to entropy, to thermodynamics, and to the second law of thermodynamics, the law that says that entropy should always increase. Now I'm going to the next part of our talk, and we're going to biology. And I'm going to make the following, I'm going to submit the following statement. I suggest that for any definition or measure of entropy that we have reviewed, there is an opposite hallmark of life. So a very good way to define what is so physically unique in a living system is to think about the examples which we have just reviewed and reverse them. So we are now going to talk about the hallmarks of life which match these definitions of entropy. We say disorder. Oh, come on. I mean, every plant, animal, even a virus is intuitively, we say, it's highly ordered, complex. That's another term that I'm going to introduce later, but it is by no means disordered. And we can show it that it's highly improbable. We are still on the intuitive side. You can understand how an animal, once being dead, is decomposing by itself. This is something that goes by itself. You will never get an animal or a living system, even very small, just being compiled by itself, spontaneously being created. We will go into it later. We say that entropy means equilibrium. Of course, we are very far from equilibrium. My temperature is, in this case, slightly higher than the environment. The amount of water within me, some chemicals, is completely different from that of the environment. We shall come to equilibrium at the end of our lives. Dust to dust, ashes to ashes. Then we shall be in equilibrium with the environment, which means death. Life means very far from equilibrium. So far from equilibrium that we are very far from equilibrium even within our bodies. There is systolic pressure, diastolic pressure. We have different kind of chemicals, compositions, concentrations of water within the cells, outside of the cells, and so on. So the whole organism and the whole, even the single living cell is very far from equilibrium between its different parts. Number of compatible microstates. So indeed, in order to be alive, there are very few, when you think about the whole systems, there are very few arrangements of molecules which are compatible with being alive compared to what arrangements could be with the state of a dead organism or decomposing organism, which then it goes up excessively high. Think about when you go to the doctor and you make some laboratory tests of your blood and urine and so on, how annoyingly being healthy means that you are within much narrower limits than being, having too higher sugar or lower sugar or whatever, iron and so on. So this is too little, this is too much. Being normal, being healthy is just in the middle. Then being alive is a narrow range, and then being sick or dropping dead is much wider. So life is opposed. Being alive means looks opposed to entropy increase also in this state. Well, of course, life is tragically reversible. Killing, unfortunately, is much easier than bringing something to life. Dissipation of heat. We, even insects or reptiles, we usually maintain a steady temperature by various methods. Heat comes to our body, heat leaves our body, but in order to be alive, we maintain a certain temperature. So this equation of dQ T does not hold for the living organisms. Decrease of energy as efficiency, that's perhaps the most impressive one. For many years, I used to teach the second law of thermodynamics in class by taking certain, there was a chalk or marker that we use today, with which you draw on the blackboard, and I used to roll it on the desk. So you have kinetic energy, and then it slows down, and then it stops. So apparently you have kinetic energy being lost. You ask the students what happened here, and then they tell you that kinetic energy has turned into heat in the table and in the surrounding air. You will never see a convergence of all these molecules converging in order to take this marker and make it roll and accelerate. After a few years, it dawned on me that I should consider the possibility, the mechanism which makes the marker roll. And these are my fingers. What is happening within my body? You have zillions of molecules, actin and myosin, within my muscle. All of them are making very tiny molecular motions, but all of them converge to the contraction of one muscle. I can give you other examples. Think about some animal, say reptile, rather than a bird, laying its eggs somewhere. So this egg is surrounded by heat from all sides. You can't do any work from this heat, right? So we humans cannot do work if you put this egg in some box where you have an equilibrium of heat. Amazingly, within this egg, this heat is being used in order to upgrade the energy to kinetic, to electric, until you have a little something coming out of this egg, small turtle or small lizard, or even in the case of the chicken, a bird. So that means there is kinetic, there is chemical energy there, but life manages to take heat, even in equilibrium, what technology today still cannot do, and upgrade it into kinetic and other forms of energy, which are of life. And if you like the subjective definition of entropy, when you say about something that it is alive, you already actually within this definition, there is actually a lot of information about the inner structure, about how the constituents, the microscopic constituents, are arranged within this organism. Now, this is all known. There is no contradiction between thermodynamics and biology. Nobody says, actually, there is that living organisms defy the second law of thermodynamics. All textbooks tell you that the living organism is not a closed system. It's open. We exchange matter, energy with the environment. So why should we expect entropy to go up within our bodies, within the organism? That's a correct answer, but it is totally insufficient. In the following sense, that everything around us is an open system. Chairs here, rocks, even trash cans, they're open systems. Matter comes in, matter comes out, energy comes in, energy comes out. They're not alive. And they don't show the increase, the beautiful increase of orderliness or complexity of the living organisms. So what I'm saying is that this answer is correct, but it is completely insufficient. It is not enough to be an open system in order to be alive. Otherwise, everything around us will be open. I don't see here anything which is wrapped with some aluminum and calcar and being completely isolated from the environment. So being an open system is by no means enough. What is unique about being alive? We need something else. And here is the thesis that I'm proposing. Now we have to bring into the discussion another notion. We have been talking about energy, we have been talking about entropy, but now let us acquaint ourselves with the notion of information. Interesting, information has something very important to do with biology and with physics. You would think that this is something technical. No, there is something very profound about information and very fruitful. So I'm saying the following, in order to show how information is relevant to studying life. Here you see a diver's watch. So if you want to dive into the sea or to the ocean, you buy this kind of watch, and it will not be damaged when you dive with it, when you swim and dive deep into the sea. Why is that? Because it is resistant to the pressure, to the temperatures, to the water. What does that mean? That means that the Swiss, Japanese guy, whoever produced this prestigious clock, they have a lot of information about the physical conditions prevailing deep in the sea. Trivial, isn't it? Now imagine how much information is encoded within a fish. The fish is even more resistant than your diver's watch to living in water, even deep in the sea, to all the pressures and so on. So what is unique to life, that is adaptation. What is unique to evolutionary theory? Increasing adaptation, we can now translate to what will turn out to be very interesting thermodynamically. Evolution is a process by which the amount and the quality and the value of genetic information increases from generation to generation. I want to show it, but before that, let's go into theoretical physics, just to the foundations of physics, to one of the most fascinating discussions and paradoxes. Yeah, just one more example. Here you see a kind of flower. It is an orchid, and it has a very interesting shape, and people who know botany know what is the function of this kind of, this coloration of the flower. It is very similar to a certain kind of wild bee, and imagine the male bee. This looks like a female bee. So imagine the male bee just looking for a mate, and then he sees what he thinks to be a female, and he mounts on her, and after a while, she is cold, she is not responsive, he's disappointed, and flies to another, what looks to be another female, and say, I met a female who was frigid, and I was unhappy, and then he realizes that it's not his morning because he found another flower like that. So he's pollinating the orchids. The male bee is pollinating the orchid's flowers, and that's trivial what I'm saying, because in the orchid's genome, there is a lot of information about the bee, about the female bee's appearance, about its pheromone, because the scent of this orchid is very similar to that of the pheromone secreted by the female bee. So once again, biology, life means being adapted to the environment. In order to be adapted to the environment, you need maximum information about the environment to which you want to be adapted. And evolution, genetics, is the process by which, indeed, genetic information about the environment goes from one generation to another and becomes more and more precise. And now I want to go to, we should just mention one of the founding fathers of quantum mechanics, but also of modern biology, Erwin Schrödinger. This is a very famous book by Schrödinger, What is Life? Schrödinger was among the founders of quantum mechanics. He has discovered the Schrödinger equation. He has formulated the Schrödinger paradox with a cat. But when he was in Dublin, he gave a series of lectures which became very famous, and the best-selling small book, What is Life? And there he said something that, although he was a very respectable physicist, he was ridiculed by many other physicists and biologists. And he defined life as a process which feeds on negative entropy. And he met with a lot of derision. There is no such thing as a negative entropy. What kind of notion is this? Entropy cannot be negative. I want to show through the concepts of information and complexity, which I will introduce later, why Schrödinger was actually correct in a very profound way. When he said that life is the living organism feeds on negative entropy. And actually, I'm going to a Nobel laureate, Sir Roger Penrose. He wrote the foreword to Schrödinger's book. I am very, may I say personally that I'm very fond of Sir Roger Penrose, who is a Nobel laureate, because he's the man who gave great publicity to the Lev Vaidman bomb testing experiment. But here we are dealing with Schrödinger's idea. And what Penrose tells you is that here we are on Earth, and here we have the sun. We have energy coming from the sun. Then we are doing all kinds of things here on Earth, doing all kinds of things within us. Actually, it is us, the living organisms, which are doing work by utilizing this energy. And then at the end, energy leaves our planet and goes back to the outer space in terms of radiation. So radiation comes in, radiation goes out, and in between there is work being done and mainly life. But here is the important thing. The light that comes to our globe from the sun has fewer photons with short wavelength. They are, we can say, more blue. Okay, few photons, short wavelength, each of them has more energy. Then we absorb them. Plants absorb them, we eat the plants and so on, and later we produce heat, which goes to outer space. This radiation differs from the incoming radiation in that the wavelength is longer and there are more photons. So you understand that the entropy of the energy goes up. We have energy with low entropy coming from the sun. We have energy with high entropy going out. So this is a way to show why Schrödinger's intuition was very correct. May I say something? Shouldn't say personal, but this is what we should all be aware of. This is to our calamity that for 4 billion years, evolution has maintained biosphere on this small planet through this process. Entropy is going up, but always leaves our world in the form of heat and goes to the outer space. We have a few billion years to live this way. What we are doing today with the ecological crisis, with the global warming, is that we are keeping with all the litter, with all the pollution and all of that. Our entropy is now chemical entropy. Our entropy is entropy of matter, and it remains here, and it suffocates us, and we may be buried by these piles of garbage. And on the top of everything, heat is not leaving us just because of the problem of the earth heating. We have now heat staying with us rather than being radiated. This is something that humanity should be aware of. But this is so far about Schrödinger's idea and about entropy. As I said, it is information that we have to be acquainted next after we discussed energy and entropy. And here I introduce to you, as I said, one of the most fascinating paradoxes in the history of physics, similar to other paradoxes, Einstein's paradoxes in quantum mechanics and relativity. This is kind of older paradox, and it's very important. And this is Maxwell's demon. You remember I said that you can lower entropy in a closed system by interfering with it. Remember the billiard ball, the billiard table? We interfered with the table, so we lowered its entropy. But by interfering with this table, we have increased the entropy in the lab or outside of the lab, so entropy always goes up. So this is the price that you have to pay every time that you decrease entropy in some small system. Entropy will more than increase in the next system, surrounding system, such that entropy will always go up. Maxwell believed, and it's interesting, it was not a paper, it was just a letter he wrote to a friend, and when such a genius writes a letter, this is just as if he wrote a book. And he said, consider the following case. And remember, in physics, we very often do thought experiments. We don't care whether there is such a system. Suffice it that this system is possible physically in order to raise an interesting question. And the question that Maxwell raised was interesting, without doubt, interesting. Here you have the box, which is familiar to you. You have gas now in full equilibrium on both sides. So you have full equilibrium both in terms of matter and energy. The gas is in equal temperature, which means that the average velocity of all the molecules is the same at both sides. You have slow molecules, you have fast molecules, so the entire gas is lukewarm. The box is divided by a partition. In this partition, there is a hole, but this hole has a door. And next to the door, there is a very, very tiny demon at the size of a single molecule. Now, what this demon is doing is sorting the molecules. You can understand that molecules now are bouncing and running to all directions. And every once in a while, such a molecule approaches the door. The demon says, I'm going to do the following. Every time that a fast molecule wants to go from the right to the left, I open the door so that it can go to the other side. Every time that a slow molecule tries to go this way, I close the door. And remember, this is an elastic collision. So the molecule will not lose any of its velocity. It will just turn back. Vice versa with the other side. Every time that a fast molecule wants to go from the left to the right, I close the door so that it bounces back. Every time a slow molecule wants to go, I open the door such that it can pass. In time, I'm going to have all the slow molecules on one side, all the hot molecules on the other side. So I have lowered the entropy. I have made the gas highly ordered during this process. The interesting thing is that the work needed to do that is very small. Either you close the door, open it, close, open. You can calculate, you can make calculations and show that the energy needed to open and close such a tiny door is negligible. So you did not invest much energy, it did not produce a lot of entropy, and you have lowered the entropy, which is impossible by the second law. Think about this example that you can see here. Here you have a glass with lukewarm water, and you're looking at it, and after a while you see that the water is becoming hot, and there is an ice cube in the middle. Can't be, by the definitions of entropy increase we formulated earlier. You can have the opposite scenario, an ice cube melting within hot water and the water becoming lukewarm. You can't reverse it, but this is actually what Maxwell's demon is doing. You have fast molecules on one side, slow molecules on the other side, which means that thermal energy now can turn into kinetic energy and you can produce work. So you have separated them. And as I said, if you calculate the physical details, you see that just opening and closing a tiny door does not require significant energy. So here we have a paradox, that the second law of thermodynamics here is a way that you can violate this law by lowering entropy without paying the price. What do you do with this? Yeah, there is a paper of ours which goes into more detail and showing something interesting about this paradox. I strongly recommend to you this anthology. You all know anthologies from literature. You know, there are anthologies of love stories and songs and other kind of travel stories and songs and so on. So there are anthologies also in science. And these two distinguished professors, whom I had the privilege of meeting many years ago, compiled a volume, Maxwell's Demon. Now it is in second and large edition, in which they said, let's take all the papers from Maxwell's celebrated letter to all the attempts to exercise it, which we are going to review now, to all the other papers, to 21st century, which derived very important lessons from it and put them in one volume, I highly recommend it. Now let's go to the resolution. We have a paradox. And how do we resolve it? We have a demon, and there has been some attempts to exorcise it, mainly four, and let me mention them. The first was by Lord Kelvin. Joseph Thomson, who formulated, was among the founders of thermodynamics, and Thomson, you know, Thomson is, historically, it's interesting. Thomson is the person who embarrassed Darwin by a thermodynamic argument that was purported to show that evolutionary theory is incorrect. It is Lord Kelvin who proved to Darwin that the time that he thought needed for the sun to exist in order for evolution to take place, by thermodynamics, it is impossible. The sun could not be that old. We all know today that Kelvin was wrong, because Einstein's relativity theory, special relativity, showed that we have, this is not fire, what is happening in the sun, but this is nuclear energy. This is not important for us, but here is how Kelvin tried to resolve Maxwell's paradox. And he did that, and this is interesting. This is a man who embarrassed Darwin, or embarrassed biology, by showing that evolutionary theory is somehow in conflict with the laws of physics. But in this case, when he tried to resolve Maxwell's demon, he, how should I say, he made biology withdraw. He made physics withdraw from, in order to give place for biology. Here is what he did. He said, the demon is alive. That demon of Maxwell is alive. Being alive means that you are actually defying the laws of physics. Today, it sounds like absolutely something which is completely wrong. Nothing in biology defies any law of physics. This has not been trivial in the 19th century, when people believed that, you know, in chemistry there was a theory, force vitalis, which said that maintained that organic matter can come only from organic matter. We humans can take organic matter and let it decompose, kill it, burn it, and let it decompose into inorganic. And it was believed that we humans cannot take inorganic matter and turn it into something organic. This is something that only life can do. Only later came the chemist Weller and synthesized urea, and he showed that the force vitalis theory is incorrect. But people used to think at that time that living systems defy the laws of physics. So Kelvin said, every time that you formulate a law of physics, do not expect it to hold for living systems. Let me give you an example. You probably noticed that some of my daughter's birds are out of their cage now, and they are flying here in the room. So you can say that the bird is defying the law of gravity. We know that it is not the case. It is due to the law of gravity that air is pressed to earth, and then the bird is swimming on the air and flying up. So we would expect, we would not take Lord Kelvin's solution, just saying that the demon is alive. This is not enough. And even if it is alive, it should obey the laws of physics. So look, we are looking for something else. Later came another physicist, von Smoluchowski, and said, well, it's not life. Let's not go into this kind of vitalism. He resorted to dualism. He said the demon must be intelligent. So intelligence is something that physics cannot explain. It goes beyond that, something have to do with the soul, with the mind. And of course, nowadays with artificial intelligence and then computer science, we understand that even something like intelligence is not going against the laws of physics. It is something very complex, which we do not understand, but we don't expect it to defy a law of physics. The first physical explanation came through Leo Szilard and Léon Brillouin, and then they said, let's go to physics in order to find the solution. Look at the demon. we thought that the demon needs energy in order to perform its ordering of the molecules, but energy is not enough. The demon needs another thing. The demon needs to know which molecule is fast and which is slow, which molecules comes from other side to other side, what is its velocity, what is its direction. How do you get this knowledge, this information? Recall that in the example that we mentioned, let me go backwards, you have the demon being in complete equilibrium. This is equilibrium of matter. Now recall that there should be also equilibrium of energy. That means that if there is light in this box, the demon is still blind because the light is now free and going to all directions. It is in equilibrium. Let me pause to explain this. Suppose that this whole room was covered with mirrors. All the walls were mirrors, and I myself would be reflecting, and the chairs and everything here would be reflecting light back. I would be blind, just as in the case I mentioned earlier, that if I am in a hot room and it's in equilibrium, I cannot do any work. I cannot get any information if there is also equilibrium in energy and light comes from all directions. The reason why you can see me now and I can see things going on in this room is because the walls are colder than the lamps, than the sources of light, and then I have this gradient of energy. This is not what happens within this closed system if it is in complete equilibrium. In order for the demon to see which molecule comes from which side, what is its position, what is its velocity, it needs an additional source of light other than the light which is could be abundant in this box. Now this additional light, you can make the calculation and you can see that this additional light brings much more energy into the system and increases the entropy. This is a physical solution. Later came Bennett and Landauer and showed that actually there is a more critical stage in acquiring information. This is a ratio of information. We don't have to go into this, but here is our lesson, and it's very important. This is how actually information theory has been established. It says that every action, every operation that you do with energy, transfer of energy, creation of energy, storing of energy, erasure of energy, a processing of energy. Each operation that you do with energy requires its minimum of, each operation that you do with information, with a bit of information, requires its minimum cost of energy. Simple example. You get your telephone bill every month, and then they're itemizing it. You have it itemized. And what the telephone company tells you is that you are using a lot of information to transfer to your friends. Nowadays, these are also movies and music and so on. There is a lot of information going on. We have to use a lot of energy in order to make this transfer of information between you and our clients. And this is why we are going to charge you. So this is something very important, the basic of information theory. For every bit of information, we shall later define what is the basic unit of information, it has its cost in energy. Information and energy come together. Now we go to biology, and we see something very interesting. Information costs energy. You want to learn something, you want to know something, pay with it with money, which means that you will use energy in order to get this knowledge in all kinds of ways, electromagnetic, electric, and so on. But that means that if you already have information, you can save energy. Here's the idea. Once you have information, you want to do some work. You can do this work with much less energy, provided that you invest this energy at the right time and or at the right place. Here's an example. These people are doing work. They are entering an apartment. They are using a lot of energy, I would say. They are using excess energy, making a lot of noise, making a lot of mess. Why do they do that? There is something that they lack. There is the key. This small piece of metal has a lot of, a lot of information in it. The person who created it had information about the lock. That means that when you don't have now to break the door, you use the key. That means that you apply little force at the right place and at the right time. Now, life is replete with such examples. Think about this guy on the left side. There's the tiger. You don't want to meet this creature in the Indian jungle. Look how much power it has in its bones, its sinews, muscles. You don't want to meet this guy. It's going to kill you and eat you. In the same jungle, you have this creature on the right, which is no less dangerous. Very little power. Muscles are not very strong. You can overcome it easily. You don't want to do that, because what it does first, it spits in your eye, then it injects its venom. Very little venom, very little energy. But now the energy goes to the right time at the right place. It has a neurotoxin within the snake's venom. In this case, it is cobra toxin, which is very similar to the acetylcholine in our muscles. You understand? The cobra has a lot of information about our physiology and about our chemistry. This is why, in order to have a kill, it exerts little energy, very little, chemical, molecular, but at the right time and at the right place. After being the bite, it only has to wait until its prey drops dead. Much less energy than used by the tiger to kill its prey. Think about this albatross. For 8 months, it's on the sea. It never sees the land until it comes to build a nest. So you might think that this poor bird keeps flapping its wings day and night and being exhausted. No, they don't do that. They look for the right air currents, for the right thermics in order to use it. So again, they are using information. One of the eminent biologists of the 20th century, John Maynard Keynes, said the following, and I was very happy when he said that. He confessed, although he was a very eminent biologist, that for many years he didn't publish this thinking, that actually the genotype is not only a description of the adult organism, but a recipe for making one given by the environment. So actually, the late John Maynard Smith would agree with me that evolution is a process by which information about the environment is accumulating from one generation to the next. So we have this notion of information, and now we can easily build this, when you want to make it mathematical and quantitative, on the earlier formulation of entropy. And here are how it goes. I won't go into the mathematical details. You have them on the slide. I'll just describe them at the logical level, and I'll try to make it visual. Suppose that I'm going to think about digits. I think that this is the best way to do it. I have 10, 0, 1, 2, 3, till 9. These are the digits that I have. And I know that the message that I'm going to get is going all through these digits. I can think even about some alphabet, the English alphabet, and so on. Before I received a single bit, which is a single digit, I knew that there are 10 possibilities. 0, 1, 2, 3 to 9. So I don't know which of them it is. This is my ignorance. It was a great idea, I think, by, who was it? I think von Neumann, who advised Shannon when he wanted to explain information. He said, base it on the definition of entropy. Because in entropy, too, you remember there are very many microstates. When you have a disordered state, there are many, many microstates. And then comes the idea of ignorance. You don't know exactly where is each of them. So in this case, you can base information on entropy by equating entropy. In order to use information, you have to define your ignorance before and after receiving the signal. How do you define ignorance? Simple. Do it with entropy. So in our case, I don't know whether it is 1 out of the 10, or in the case of the alphabet, which of the 24, 26 letters I have. So that's all I need in order to define my ignorance. And then when I get the message, it shrinks ideally into 1, so I have certainty. This is how you base information on entropy by using entropy for your ignorance. So I'm not going to go into the mathematical details, how you equate Boltzmann entropy with information, how you make it even more refined in case you have different probability for different letters or digits and so on. Now here is a question which is somewhat philosophical, but has a great scientific bearings. How do we measure information? So from thermodynamics, we got the equations of entropy in order to measure the capacity of the information, the quantity of information, the precision of the information. These we can all do. What about the value of information? Here, some of the leading pioneers in information theory said this shall always remain subjective. I think it was Brillouin who said that take Einstein's equation E equals mc squared, replace it with any other string of such letters, and it will have the same information content. In other words, he believed that information theory cannot tell you anything about the importance or the value of the information. It just measures its length, its precision, and so on, its capacity. With all due respect, I want to take exception with that. And I think that scientifically, we can also measure the value of the information. And here's one way. Take Maxwell's demon. Suppose that you get the information. Suppose that you have some knowledge prior to that about the motion of the molecules. Then, if you have this information, you can indeed sort you can sort the molecules without investing so much energy that you would need in the case of being ignorant about their motions. Think about think again about the example of the tiger and the snake and the cobra. The cobra performs in many cases the same amount of work being performed by the tiger with much less energy, with much less force, with much less work, just by using information. So how about this? Give me the amount of energy needed to perform a certain work with the information and without the information. Let me go even to the much earlier example. Remember these guys smashing a door? So they are doing some work, entering into the room. They use a lot of information. Now give them the key. They do the same work, which with much less energy. I would say, and this is my proposal here, to the best of my knowledge, it is original, that the value of information can also be measured in the same thermodynamic terms by comparing between the energy that would be needed to perform a certain work with that information or without it. This may turn out to be important in what comes later. Now, let me say something about, and now we are going to evolution, how evolution itself is a kind of information processing process. That is, information is a process by which, evolution is a process by which information from the environment is being absorbed and then being processed again in order to refine it, to make it more important. I'm going to show you the difference between signal and noise. This is the problem that we have usually when we want to extract information from a certain noisy environment. We have signals, we have information, but we have also noise. How can we represent them here? I'm giving you many cards which are transparent. On each of them, you see a pale, the word signal being very pale, and the word noise being somewhere also on this card. Now, the word signal is always at the same place, at the center. The word noise can appear on this side, on that side. It varies. So this is what makes it noise. It is just not constant. It is very random. Suppose that I have many cards like this, and now I have made them even more pale. And now I place them one on the top of the other. You barely can see here either the signal or the noise. So you place them one on top of the other, and you see something very nice. You see that the signals strengthen themselves whereas the noise kind of cancels itself. It doesn't exactly cancel, it adds up in a much weaker way. So much so that at the end of the process, you can see the signal. What I want to show is that this is what evolution is doing. So this is Schrödinger's formula of showing how a signal is extracted from noise. So the signal, the information would be the S, the noise would be the delta S, and you can see that when you add them together many times, n times, they add in a different way. The signals add in a very strong way, and the noise just in a much weaker way, such that you can separate between them. You can see that in evolution. Many times you can see, we wonder, how come that in order to create amazing structures like our eye or the bird's wings, how could very small mutations help us? At the beginning, they seem to be of no help. You can think about a wing of 1 millimeter. It doesn't help the bird at all, or the reptile. We know that there's been a leg which later gradually turned into the wing with very small mutations. How do these small mutations work? This is very similar to the process that I described now with the addition, with the superposition of cards. Imagine these rabbits. These rabbits multiply, and they have, as you can see, a few mutations. Some of them are brighter, some of them are darker. The difference could be very, very small. So you would think that it doesn't give you any advantage whatsoever if it's very small. Now suppose that something has changed in the environment, and there is always snow in that place, or this is a population that migrated to an island where there is a lot of snow. You can see how a very minute change in color, when you're talking about large numbers, turns out into advantage in the following sense, that most of them are being wiped out. Very few remain. They may go extinct, but if a few remain, the chance of one rabbit which is slightly brighter to meet a male or female of having the same mutation is slightly larger because all the others are gone, which means that now when you again have mutations, some of them can be darker and some of them can be brighter. The brighter ones are somewhat, they outnumber the darker ones. Then you can see how very slowly the entire population moves from dark rabbits to having a population of white rabbits in the new noisy and in the new snowy environment. Again, what I want to show is that evolution is doing something similar to that of the antenna. You see, each of the rods of this antenna gets both signal and noise coming from the source of the information, but from all other sources which are a noise, and it manages to isolate the signal from the noise. This is an example which I like. It takes us to philosophy, but there is something very profound. It turns out that what we know in science actually has been discovered, and we shall come later to that, by evolution. That is, being an organism, whether you are a plant or a bacterium or even a virus, means that you are utilizing a lot of principles of mechanics, electricity, chemistry, optics, acoustics, whatever, even to the point of discovering the laws of mathematics. There is a debate between philosophers whether mathematics is an invention of the human mind or whether it is something there in the universe that we are only discovering. How about this example? Think about the cicada. Here in North America, you have several species of cicadas. Some of them are known as the 13-year cicada. Why do they call it the 13-year cicada? Because for 12 years, it's a maggot living underground. At the 13th year, they come out, they mature, males, females, make an orgy, lay eggs, multiply, and then they die. Now you have to go through another cycle of 13. So this is the 13-year cicada. There is another species which is called the 17-year cicada, which is similar. 16 years as a maggot, 1 year multiplying and then dying and beginning all this together. Now, surprise, we have in North America 7 species of these cicadas, whether they're 13 or 17. And now if you know some evolution, you see all these species, and I ask you, which of them have a common origin? And I guess I guess I know what answer I'm going to get. You will say that all the 13 years species have a common ancestor, and all the 17 years have another ancestor. Not so. Here is a surprise. They are related. These two 13s are related to this 17. This 13 is related to this 17, and this 13 to this 17. They have 3 common ancestors, so that means that 3 times evolution came to the 2 pair of solutions, 13 and 17. Why is that? Well, we understand that 13 and 17 are prime numbers. And we understand that in evolution, you have the following mathematical problem. If you're an organism multiplying not every year, but it takes you somewhat longer, then you don't want your life cycle to coincide with that of another predator, which means that even if your life cycle is 3 years and his is 6 years, in time, that predator will learn how to match their own life cycle to yours, such that every second generation, their offspring will feed on yours. So you don't want that. The best way is to look for some prime number. And the hypothesis is that probably these miserable cicadas tried the 3 years, 5 years, 7 years, and some predator got them. They went perhaps to the 11 years, and somebody got them. Now they are stuck with the 13 and 17, and they don't want to disturb one another. So this is how evolution came to 3 times to this pair of prime numbers, which are very large, in order to escape predators. This is something to think about. When I use it in favor of the thesis that I submitted to you now, that evolution is a process by which information is gained from the environment, I would go to say that this information is becoming more and more invariant to the point that it is completely abstract, just as we human beings have created science and mathematics. So with this, I'm closing our discussion of information, which was brief, but this is what we need for our discussion. And I want to introduce the next and last notion needed for our talk today. So we have discussed entropy, which is disorder or order, and gave it all the definitions, mathematical ones, randomness, equilibrium, and so on and so on. Then we defined information as being based on entropy in order to understand it, and in order to understand its physical significance. So information, just like entropy, has a mathematical side and a physical side. And it's time now to acquaint ourselves with a third and last notion, which is complexity. You remember that I promised you that I'll give a mathematical definition of order, not leaving it as something subjective. I can see that this closet is ordered and this is disordered intuitively, but I want now to have a mathematical definition of that. And that will help us very much to define also this important notion of complexity. So I'm going to use sequences of digits from 0 to 9. It will be very convenient. I'm making a sequence of 100 digits. I divide them into 10 compartments, and here you have sequence A. First of all, intuitively, you say sequence A is completely ordered. How do I know that? If I tell you that just I mixed all kinds of digits together, and just by itself, by complete coincidence, I got all the ones, all the zeros on the first 10, and then all the ones in the second 10, and twos, and so on, you will tell me, get out of here. I don't believe you, and you will be correct. So I say that sequence A is ordered, and then we shall look for the mathematical measures of this orderliness. Here are 3 measures of orderliness. They are due to a biologist named Lila Gatlin, whose book I like very much. And the first criterion is divergence from equiprobability. Do you see that for any digit along your sequence or within any compartment, do you see that there is an equal probability for each of the 10 digits to appear there? If they have equal probability, this is disordered. As you diverge from it, you are highly ordered. So now mathematically, I understand that sequence A is maximally ordered because its divergence from equiprobability is the highest. There is no equiprobability in the first compartment, in the second compartment, no way, only zeros, only ones, only sevens, and so on and so on, okay? Second, divergence from independence. Given that you know one digit, what are the probability for the other digits to be 3 or 8 or 0 or whatever, given that you know the digit before them or after them? Once again, if they are completely independent of one another, this is a disordered, completely random sequence. If there is some dependence, then it is ordered, and we can see again that A is maximally ordered because the dependence on the digits on each other within every compartment and between the compartments is maximal. Third criterion is due to Gregory Chaitin. Can you compress this sequence to a much shorter algorithm? No problem with A. I say I type 0, then small 10, which means repeat it 10 times, then 1 with little superscript 10, 2, 3, and so on. You see, I have compressed these 100 digits to something much smaller, almost 10, slightly more than, a few digits. I can even give up, say, 1 and then 0, and then the next compartment will be add only 1, so I can compress it even to very few digits. So by the three measures, A is highly ordered. Now let's go to B. Don't bother very much. I brought it from some random generating machine. So you can see that the divergence from equiprobability is very small, from independence is very small. They are the equiprobable, independent. You can compress, you can't compress the sequence into something shorter. Every once in a while, if you see 2 sevens or 2 zeros, you can compress them. But if you compress it, still the shortest algorithm to do that, and we call this compressed, this sequence of compression, we call it an algorithm. The shortest algorithm is just as long, almost as long as B itself. So here we have two opposites, one completely ordered, one completely disordered, and we see 3 very useful criteria to define them, what is ordered and what is disordered. This is very rigorous, nothing subjective. This is simple mathematics. This is A and this is B. What about C? C, there is something intriguing about it, because within each compartment, I have an equal number of the digits, 1, 0, 1, 1, 1, 2, and so on. So they have the equiprobability. There is no divergence from equiprobability within each compartment. There is a lot of divergence from independence. If I know one of them, I know the one before and one after. So there is a conflict between the first 2 measures. And then, of course, when I come to redundancy, no problem to compress the sequence, the whole sequence, to something very short. So sequence C is not disordered. It's not completely ordered. There is something interesting about it. What about D? Some of you who know mathematics can understand that I cheated you. I took the phi, and then took out the first pre-decimal digit, and then I could do it with pi, but then there are many smart students who understand it, so I took the phi. Here I have something which looks completely random. I mean, by divergence from equiprobability, divergence from independence, no divergence. You can't, if you know one of them, you can't infer from one digit what is going to be the one before and after. So by the first 2 criteria of Gatlin, it looks completely disordered. We know that it is not random, that it is phi, and actually we know that we can compress it. There is an algorithm how you produce phi. And this is the one. I believe it is due to Euler. So sequence D is not random. There is a lot of information in it about phi, and we will talk about it. But sequence D is complex. We now encounter a notion which is different from order and disorder, and then also from randomness or whatever all the other accompanying definitions. Here we encounter something called complexity. And immediately we understand that complexity has a lot of value in biology. Many biological structures are complex. But now we want a mathematical definition of complexity. And here we go to Bennett, who said something very genius. He said the following. He said, don't mix complexity with order. Many people did that. I did that in a certain paper, which was some 30 years ago, severely attacked in the Journal of Theoretical Biology. A man named Hubert Yockey wrote an, shall I say, a nasty paper. The late Hubert Yockey wrote a nasty paper on a paper which I wrote, and he was correct in saying that he didn't mention the word complexity, but he said that I misused the word of order. So how I'm going back to our sequences, you see that there is something very unique about D, because phi is unique, because pi is unique, E is unique. There are numbers in mathematics, irrational, very long, which are very, very important. They are not random, but they look random. Actually, there is a theorem by Chaitin that says that you can never tell whether what looks to be random has a shorter algorithm, and there is some complexity, and that it is actually complex. Now, what Bennett says is the following. Complexity is orthogonal in some senses to order, to the axis of order. Look at the graph below. I represent order on this direction, okay, and complexity on this direction. And you see something interesting, that complexity reaches its maximum between order and disorder, between high order and low order. For this, let me go again to our sequences. You agree that A is completely ordered, B is completely disordered, but A and B have something in common, although they look completely different. And here now we go from mathematics to physics, and then, of course, it will be highly relevant to biology. So far, we are discussing only mathematical relations between digits. But now comes something physical, and here it is. What is common to A and B? A has a much shorter algorithm, right? I can compress it to 10 zeros, 10 ones, and even just define how you go from 0 to 1 to 2 by adding 1. Easy. B cannot be compressed to a shorter algorithm. Its algorithm, even if you compress the 2 sevens here and there or whatever, it will be almost as long as B itself, the algorithm. So one of them have a very short algorithm, the other have a very long algorithm, but they have something in common. You don't need much computation in order to produce them. You don't need much computation in order to compress them. If I ask you how you compress A, it's easy. If I ask you how you compress B, you say you can't. You just, type it again with a few redundancies. If I ask you how to reproduce it back from the algorithm, it's easy with A. You just print again the zeros and the ones, and you produce it. With B, you just copy it. What is common to both order and order is that you don't need a lot of computation in order to compress them or to produce them again. It is completely not so with D. It looks like B in looking disordered. But in order to compress it, you need a genius like Euler, some mathematician, same with pi and others. And in order to reproduce it again from this formula, you need a lot of computation. So you see, here it is, complexity reaches its maximum where you need the greatest computation, which is far from high order, somewhat closer to low order, but it's not order, not disorder. This is complexity. And this is why it is so important for our case. Suppose I walk in the field and I find a diamond. I'm a very happy man because I found something which is completely ordered, only carbon molecules, and they are so beautifully ordered in one crystal, almost pure carbon. I find a rock nothing to be happy about. It's not very ordered. It's a mixture of all kinds of chemicals with all scratches and holes within it, and nothing ordered about the internal arrangement of the molecules. And then I find this onion. So same size. It's not ordered like the diamond. It's not disordered like the rock. It is complex. You have to study its minutest cells in order to see that they repeat themselves and they correspond to one another in a very important way. So what's important about the onion? You understand that the diamond doesn't tell you much about the environment. There is no much information about the environment by the diamond. It tells you it was brought from South Africa or India, so from a certain mining. But there is not much information about the entire environment. Now think about the rock. The rock tells you something. It gives you some information about the environment in which it was created. Its chemical composition, the holes, the depressions, the scratches on it, fine. The onion has information about billions of acres all over the globe, during millions of years. Within it, there is information which has accumulated, which has made it adaptable, made it resistant, capable of growing in any place, almost, save Antarctica or the desert where you can or Alaska, when you can plant such onions and grow them. So it has more information and it is more complex. So let's think about these kinds of, now that we know what is complexity, let us think about various kinds of information that we see in, say, in the plant kingdom. I would say that this creeping plant, Luis, do we see the mouse going on the screen? Or
yes,
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 okay.
We can see it. Yes,
very good. So you can see this creeping plant. Here you see the rock, which has some information just about its immediate environment. You can see this creeping plant. The shape of the plant gives you some information about the wall on which it is creeping. That's nice, but it's local information. Now look at this tree, the fir. There is information in it, but the information in it is stored within these statolites, which are somehow immersed within the liquid within the cell. This is how the tree feels gravity. So the information it has, it is not only something like pi or phi, which many plants and many animals have in their genome when they create shapes that comply with geometrical notions, like being spheres, or the examples I mentioned earlier, Fibonacci series, and so on. What the tree has is what Newton has discovered, the very notion, the very constant of G, which is invariant all over our globe. So I would say that information during evolution is becoming more and more invariant, rather than information about this environment. And during this period, we have information which holds for larger and larger environments for longer and longer periods, millions of years actually. This philosophically is not much different than human science. And there was a philosopher named Karl Popper, together with the zoologist Konrad Lorenz, who formulated the philosophy called evolutionary epistemology. And they've shown beautiful examples, parallels between the growth of knowledge in science, hypotheses, refutations, confirmations, and so on, and evolutionary theory. It looks like every organism is a scientist, and that during evolution, every organism is learning how to recognize the most basic and invariant laws of nature to use it for its organismic. This is organismic knowledge, whereas we humans, from one generation to the other, accumulate extra-organismic knowledge, information, but they grow following the same rules. So let me summarize. We discussed entropy and order, and based on entropy, we discussed information and complexity. Now I would say we have been asking, can we assign mathematically, can we quantitatively assign value to some information, whether it is important or not, whether it is useful or not. Here is another one. When you compress a very complex sequence to a short algorithm, you use a lot of computation to do that. You can do it only to something very complex. That algorithm has very valuable information. The more computation is needed to create a short algorithm from a large sequence, that is another measure of the value of the information. I should one day, and in a paper, just give a precise mathematical expression for that. Information's value, so information is required to create complexity. This we will see later in the following examples. Information value is the highest when the algorithm, the shortest algorithm gives you a very complex sequence or structure. Now, recall, and this is the more general conclusion, that nature around us is very complex. It is not completely ordered. It is not completely disordered. Have the universe being completely disordered and random, there could be no life in it. We see that it is not completely ordered. There are many unexpected things, a lot of randomness. The laws of nature are the algorithms showing the hidden order within our universe that our genome is taking and taking advantage of in the process of evolution. Think about every time that you go to pick mushrooms. If you know to do that, don't do it if you don't have somebody who knows to do that. But imagine people who know how to distinguish between poisonous mushrooms and edible mushrooms. They go and use their knowledge to do that and to add to their health, eating something very tasteful and healthy. Try to imagine, and I'm not being cynical, how many generations of our forefathers died in agony of being poisoned, having vomiting and diarrhea and all that, and in their last breath saying, "Don't eat this red mushroom, it is poisonous." So actually, what is evolution? We are lawful Maxwell demons. We are just like Maxwell's demons. We are doing little and achieve a lot. Just like this demon opening and closing a door. But we are doing it lawfully. We have information, and for which this information our forefathers, our ancestors have paid dear price. Think about all the dinosaurs who went extinct in order to make us capable of coming to this world, not going again through trial and error, but using the information that they have used in order to increase our complexity. Let me finish by saying that the importance of thermodynamics to biology is far from being exhausted. We are just at the very beginning. There are several examples and when you take into account the notions of information, complexity, you can do a lot. I can mention only here one group of works by a team of Russian scientists, Alexander Zotin and Lamprecht and Zotina. They have been a team, and for many years they produced papers which I think have been slightly forgotten. What they showed is that when you take a certain very simple thermodynamic value, say dissipation of heat, very simple, you don't have to go into the details, and you compare various organisms along the evolutionary scale. It's very complicated because you have to take into account the size of the organism, its weight, its volume, and so on. You have to control for all these. But if you do that, and you compare, say, an elephant with a crocodile, or one mammal with another, or one bird with another, birds with mammals, with reptiles, with amphibians, and so on, you control for the size and for the weight, you see something interesting. By the production of the heat, you can define their evolutionary scale, how evolved they are. And they actually argue, I don't know how correct it is, that they were capable of defining between different groups of mammals, say the monotremata, the platypus in Australia, which still lays eggs, which is a very primitive kind of mammal, and marsupilia, and then other more advanced mammals that we have all over the world. They claim that what paleontologists have taken a lot of labor in order to construct the evolutionary tree of their development, they can show it just by heat production. It looks rigorous. I don't know, this is the line of research that I think that people should return to. And it shows you how with thermodynamics, you can sometimes, without going into the details, you can draw far-reaching conclusions about biological processes. I would even argue that measures of temperature, if you measure my own temperature, I believe that I have a slide of this kind somewhere. Okay. Suppose that you were taking a infrared picture of me. You would see different places in me which give you different colors, infrared colors. That is enough to know where my brain is, where most of the work is being done within my body, without going even into the details. So with this, I would conclude this lecture, which I confess has been very long. It is a kind of introduction of the importance of thermodynamics to biology and the thermodynamic basis, the basic thermodynamic principles underlying biological phenomena. I'm going, thanks to Luis, I'm going to give a sequel to this talk in which I'm going to discuss a much more specific hypothesis, the ski lift hypothesis, in which I'm going to make use of some of the basic principles mentioned in this talk in order to shed some, I believe, novel light on some biological phenomena. Many thanks. I understand from Luis that there is going to be a session of questions and answers. You may even forward them to him and we can form a dialogue. So many thanks for listening to me so far. Thank you very much, Jose Luis, for this opportunity to talk with your distinguished audience.
Well, thank you very much, Professor. It's been a delight. And I just want to make one final reminder to listeners that we will place all of the relevant links in the video description. We invite you to take a look at those links. So thank you very much, Professor, and we'll see you very soon.